Okay, so welcome back. This is part 3 in our series of videos where we're showing you how to write programs to control your bench instruments. And we're going to be using Visual Studio, Microsoft Visual Studio. In the previous videos, we're showing you how to program your signal generator and how to set up a Microsoft Visual Studio solution that will help you to also program your oscilloscope. And we're using as an example this application here, which is performing a SFRA or sweep frequency response analysis. Now this is just one example of things you can do once you've learned how to program your bench equipment. And this basically takes a sine wave. In this case, we're feeding it into the winding of a transformer and varying the frequency. You can see here we're plotting out in real time the voltage as we feed in series this sine wave into our transformer winding and measure the output voltage as we vary the frequency. You can see down here we're going from 10 hertz to 10 megahertz, and we're in real time measuring the output voltage and plotting it on this log graph. So I encourage you to look at the previous videos. We have a lot of videos talking about programming in Visual Studio and C#, doing engineering applications, and this is just one of them. In this video, we're going to finish up our Visual Studio solution, writing the code to show you how to program your oscilloscope using Skippy commands and networking, and how to grab these values that you see plotted here, these voltage values, out of the circuit via the oscilloscope and plot them on this graph. So in this video, we're going to finish up the code to do the oscilloscope programming. So here is our Visual Studio C# solution. And again, I encourage you to look at the previous videos. We show you how to get this. We downloaded a basic solution called Simple Read Write, and we show you how to do that previously. And then what we've done in previous videos, we've showed you the basics of this solution, the using statements, all of this stuff, and we showed you the main, and we also showed you some of these methods we're using. We've got some methods here and some event handlers. And in the previous video, we talked about how to open the COM port, configure the signal generator, and read the frequency. It's a text file that's going to define what frequencies we want to set our signal generator to vary the frequency. And this shows us how to read a file that defines those frequencies. What we're going to do in this video is we're going to look at the event handlers that really do all of the work. We've got, as you can imagine, we've got this timer event handler, system timer, that every second or 2 seconds is actually going to set the signal generator frequency and then measure the voltage. So this is the big workhorse. There are two existing event handlers in this Simple Read Write solution that we downloaded, and these are from the NI Visa solution from National Instruments, and these are existing. Basically the click button to open the session and close the session. As you can see here, if we want to open up the session to connect with the oscilloscope, we've got this button and then this button. So these are the event handlers for those buttons. And these, we haven't changed these at all. This is basically what we got with that solution that we downloaded. So no change there. I added a few comments as I usually do. The button COM open click is just running this method we talked about last time, which is open COM port. We've talked about opening a COM port in C# many times in many videos. So this is pretty straightforward. We talked about it before. And then the close COM port button. So it's basically these two buttons, the event handlers, and very simple code for those. Then we have two really important buttons, and those are the Run SFRA, the event handler for that, and then, as we said before, the timer 1 tick, which does the setting and the reading. Okay, so first let's look at the button SFRA click event. Here I've just enabled and disabled some buttons. I like to do that. If the session is closed, we don't want to have a close button enabled because all you can do is press the open button. So we're kind of directing the user by enabling and disabling buttons. And then the next thing we're doing after we start that sweep frequency response by clicking the button is we read the frequency file we talked about last time. It's that method up here that basically just reads the text list of all the frequencies we want to scan. So we already talked about that. We're all set. Next thing is two lines that I extracted out of the existing solution from National Instruments. And those are the two lines that we need to send a command to the scope. In this case, we want to set the scope range to 2 volts. And we talked about that previously. And the two lines we need are, we define the string of the text that we want to write to the scope, which basically has this Skippy command we talked about previously, where we set the channel 1 scale to 2 volts. So we define the text to write, and the way we do that is the way it was done in the basic solution from National Instruments. Is there is this method up here in the methods to replace common escape sequences, and you feed it a string, and insert common escape sequences, you pass it a string. And that's basically what they use to prepare whatever Skippy command, prepared into a format that can be accepted by the scope. So I didn't change anything. I just said, here's the Skippy command. And as they do, you feed it to this replace common escape sequences, and then go to this mbsession.rawio.write and send that text to write. And that will send it to the scope. And this MB session you can go through. This basically is the connection to the oscilloscope. So we're not going to go through that in detail. I encourage you to look at the existing code. They talk about what the MB session is and all that. But really, to send a command to the scope, you just define the Skippy command, which we have here, and feed it into this method they have, and then send that to the scope using this line, mbsession rawio.write. Pretty straightforward. We start the SFRA by setting the scale to whatever scale we want to make sure it's sensitive enough scale. And then what we do is we set the interval of the timer, the system timer, to what we want. Timer 1 interval is going to be whatever the user defines in this time step text box. And we're going to default that to 1.5 seconds. You can see we start up this application with a time step text is 1.5. So by default, it's going to be 1.5, but the user can change it. So here we just take that time step text, convert it to double, and then multiply times 1,000, because the interval in this system timer is in milliseconds. So we're going to enter it, say 1.5 seconds times 1,000 is 1.5 thousand milliseconds. So we take that, convert to int32, and that defines the interval of the timer. And then all we have to do is enable the timer, and the SFRA is going to start. That's basically it. You start the timer, you configure everything, and you're all done. So now, as you can imagine, all of the work is going to be transferred to this timer event handler. All right, every 1.5 seconds, it's going to call this event handler, and it's going to set the frequency and then read the peak-to-peak voltage from the scope. And here's the code in this timer event handler. So I'm going to go through some of this. If you want to copy it, just pause the video. But the timer 1 tick, we're defining a string called the present frequency, and we're going to increment that. We're reading in each frequency we want to set the frequency generator or the signal generator to, and that's going to be a string. And then volts is going to be the peak-to-peak voltage reading as a double coming from the scope. The first thing we're going to do is required because we're using a logarithmic graph. And if we have the frequency index, which steps through the frequencies, it's going to go element 0, 1, 2, 3, 4, 5, whatever. If it's index 1, which means it's the second element, then we are going to take our chart and define the x-axis as being logarithmic, okay? And that's required in order to set the logarithmic scale. You've got to have a couple values. So here we've got a couple of values since it's a element 2, and we're setting that to be logarithmic, all right? Now this next one, if the index of the frequencies it steps through is the frequency, if it's less than the total frequency values of all the count of all the values we're going to step through, in our case it's like 300 values, as long as we're within that range, we're going to do this. And what this does is it basically sets the signal generator, the func gen port, which is our COM port, it basically sets the frequency to the present frequency in that list and moves on, okay? So the present frequency, what we do is we take this frequency values with this freak index, right? We're stepping through this freak index, and the freak values times 100 and convert that to string, and that gives us the present frequency. So here's the list of frequencies we read in, multiply times 100, because the signal generator takes the values and assumes they're times 100, and that is the present frequency. So then we append that value to this text box just to give us some feedback on what the present frequency is. So we append the text, freak vals, freak index with a carriage return and line feed, all right? And then we actually write that value, that present frequency, to the func gen port, the serial COM port. And we use this command we talked about before, W23, which writes the frequency to channel 1, plus the present frequency, which is this string, plus comma 0 with a period, and the carriage return and line feed. We talked about the syntax we need for the function generator, but that's basically the command structure to change the frequency to this present frequency. And then what I've done is I've done a read for that port, because when you send a write, it returns an OK string. So I'm just reading that. I'm not doing anything with it. I'm just reading it just so I know what's there. And then what I'm doing is I'm doing a thread.sleep, which you may or may not need, but it's something you need to think about. We've got this command delay milliseconds, which we defined previously. And basically, it allows us, after we've sent the command, to delay a bit to let everything settle in the signal generator. I'm going to set mine to 0, but you can, it's just there if you need it. So now we have set the frequency of the signal generator. So what do we need to do next? Well, we need to read the measured voltage from the oscilloscope. Here we have a test. If you've reached the end of the frequency range, turn off the timer to stop the scan and plot the final data point. And that's what this is. If the frequency index is greater than or equal to the total count of those 300 frequencies minus 1, then disable the timer, timer run enable.false, and then append the text and just tell the user, give them some feedback that the timer is off. So that just stops it if you're done with the SFRA. Now, the next thing we're going to do is we're going to do a try and catch. And the try is going to send a skippy command to get the V peak to peak. And again, we're going to use the same format to send a command to the scope. We get the text to write, replace common escape sequences, and this is the command, the skippy command that we talked about before, to measure the V peak to peak in channel 1. And it's measure item ? Which says we want to know what's the answer, VPP, channel 1. So we've got the string, and then we use this MB session to write that string to the scope. And then we can again use this thread.sleep if you want to delay, to wait for the oscilloscope to settle out. Again, I'm going to be using 0 probably, but we've got that in case you need it. And then what we're going to do is we're going to read the response, which is an mbsession.rawio.read string, and that is the V peak to peak that is returned from the scope. So now we've got a string with that, whatever format it is, and next what we need to do is we're going to have to parse that into a double, which corresponds to the actual peak to peak. Now this is going to be in a scientific notation, this V peak to peak coming from the scope. You're going to have to check what your particular scope has, but we need to make sure that we change it into a usable double using this try parse. So the triparse, we've got the V peak to peak is the string that's coming in. And here is a bunch of stuff you're going to have to add in order to get a scientific notation out as a usable double. So V peak to peak is the string coming in, numberstyles.any, comma, culture info dot invariant culture, and then out is volts, which means volts is going to be the double representing this string peak to peak. So then we're going to give that value to this text box as feedback to the user. We gave it the frequency feedback, and now we're going to give it the measured voltage feedback. We've got read text box out of pen text, volts to string with character turn line feed. So now the feedback is going to be what frequency we set the signal generator to, and the next one is going to be this, what volts did we read from the oscilloscope. So now we've got the volts and we know what the frequency is. We also have to check to make sure that the scale of the oscilloscope is appropriate. We're not clipping the voltage, or we've got to make sure it's a sensitive enough scale, as we talked about before. So now that we've read the volts, we're going to use that to figure out what's the correct scale. So if volts is greater than 0, that's kind of an error checking, just to make sure we have a positive voltage. We're going to call this method called set scope vertical scale and feed it the volts. And we'll get into that in a bit. But basically it determines, based on the voltage, what scale is appropriate for that voltage. All right, very simple. If it's not, then we're going to say it's a glitch. We're going to increment the number of volt glitches. We're also doing that in this set scope vertical scale. So this just says if it's a negative, it's a glitch. And then we're going to increment the number of glitches right down here, number of bad readings. We also want to check if the latest voltage reading is too much different from the previous reading, indicating it's a glitch. Now you may not need this, but we've also got this, you feed the voltage in here and we go to this method, check input volts, and it checks to see if, suddenly you get a weird reading. You may want to, either discard the reading or filter it by, taking the average of the voltage or whatever. Once those are done, once we know we've got a good voltage reading, we're going to add the latest frequency value to this incremented freq values that we're going to plot, and then we're going to chart those values. Keep in mind when we do this check input volts, we're going to make sure we've got a decent voltage reading of volts. It's going to clean up this reading. So now what we can do is we can plot the X frequency vals, and here we're setting the correct volts. And previously we're taking this volts and setting it as this Y volt vals. So at this point we've got a good frequency vals and a good Y volts vals. And all we have to do is we have to do a points data bind XY with the two values to update that logarithmic scale. And we've talked about this in our C# charting series. I encourage you to take a look at that. And then we just increment the freq index. Now, if it doesn't work, we're going to have this is a try catch, and we just throw up a message box that gives us the error message. And then here we have a finally that we're just copying from the existing National Instruments solution where they do cursor.current equal cursors.default. You can look into that. So really pretty straightforward. The SFRA stop, I'm just closing the func-gen port. Setup control state, this I got from the National Instruments solution. NB session dispose. We disable the timer, and if the func-gen port is not open, then we change a couple of these buttons, and then we're all set. All right. So that's about it. A lot of the work is done in this timer tick. We'll briefly go into these two methods we talked about before, which is check input volts and set scope vertical scale. So we feed the measured volts into the set scope vertical scale, and all we do is we check. Is the voltage less than 2 volts? If so, we're going to set the scale to 0.25. Is it between 2 and 4 volts? If so, we set it to 0.5. Is it between 4 and less than 8? If so, we set it to 1. Is it between 8 and less than 16? We set it to 2. Is it greater than 16? We set it to 5. And then we can do a thread.sleep. Again, since we're sending a command to the scope, you may want to do a thread.sleep. So really, it's pretty straightforward. We just check what's the range, and if it's in that range, we set it to, we do a skippy command. And again, we're using these string text to scope, mb session raw.io.write, and that's all you need, these 2 lines, to define the skippy command that you're going to send to the scope and to actually send it. So that's basically it for your scope. You might want to do it differently, but that's should give you a good idea about what's going on. And then check input volts. This is check to see if the volts read from the scope is significantly different from the previous reading, indicating a possible glitch in the signal generator output. If it is significantly different, assume it's bad and therefore replace it with the previous reading. Also, don't check the volts reading versus previous reading if there are no previous readings, all right? So it's basically a if and else. If the frequency index is greater than 1, in other words, we have 2 readings, at least 2 readings, because, we can't check the latest reading versus a non-existent previous reading. So we got to make sure there's a previous reading. So if the index is 0 and then 1, then we can check versus the previous reading. So we first figure out what's the previous value, and that's the freq index minus 1 of the Y volt vals. That's the previous val. The difference is the difference between the present reading and the previous reading. And the percent change is we do a math.absolute to get the absolute difference of the difference over the previous val. So it's the percent change from the previous multiplied times 100. And then I've got an if-else inside of this that says, well, if it's, say, greater than 60% difference, then let's assume it's a bad reading, and we're just going to take the previous value and use that instead of the latest value. So if percent change is greater than 60, you can use whatever value you want. I just threw a number in there. We'll say that the present Y volt vals is the previous value, not the latest value. All right, so we're just replacing the latest value with the previous because we know the latest value is not right. We're incrementing the number of voltage glitches to increment the number of bad readings. And then we're feeding to the text box what that string is. If it is not greater than 60%, we'll say, okay, that present reading is a good reading, and we're adding that to the Y volt values instead of the previous value. So very straightforward. Now, if we're on index 0 or 1, we're just directly adding the present reading. We're not checking it against the previous, all right? So really, pretty straightforward way, but it's really important, however you do it, that you check the input value. In my experience, the signal generator occasionally will go goofy and suddenly drop to 0 or give us some weird readings. So I really encourage you to, go through and do something like this when you get an input value. Check it to make sure it's reasonable, all right? So again, these are existing from the National Instruments: set up control state, replace common, insert common sequences. So that's about it for this application. Again, we basically use the National Instruments Visa solution, C#, and just modified it to add this functionality. Okay, so that's about it for this one. I encourage you, if you're liking these videos, hit the like button, subscribe, hit the bell notifications, and most of all, please let others know that we're here so we get some views. Really appreciate it. Otherwise, take care. Have a really good day. Thanks.